right. So I want to highlight some of the things that you probably already have watched my video, which is awesome. When I say it's awesome, I'm not saying the video is awesome. I'm just saying that it's awesome that you watched the video. So section 1.6 is on something called limits at infinity. This is different than what we did when we looked at the last section. The last section, which was 1.5, was entitled Infinite Limits. In fact, when you look at that title and then you look at today's title, you might say, well, man, Mr. Allen, this seems like almost the same thing. Actually, no. These are very different things, and hopefully I'll make that apparent today. So objectives, I'm not going to go through those. I did that already on the video. But what is this thing? What is this thing right here? What do we call that? We call that a horizontal asymptote. And the question that kind of starts this out is how do we figure out what that horizontal asymptote is? Well, if you had your graphing calculator and you started looking at, let's just go this direction. Let's say that x is increasing without bound. So it's starting at 0, then 1, then 10, then 100. It's going bigger and bigger and bigger. In other words, x is growing without bound. What is happening to the y value? Well, you'd think maybe the y value would be growing without bound, but actually it's approaching a number. What number does it appear to be approaching? It appears to be approaching 3. Similarly, if you go to the left of 0, in other words, you start decreasing without bound, what happens to the y value there? It goes to 3, which kind of makes sense. Guess what the equation is for this blue line here that's dashed? Y equals 3. In other words, as this function goes further and further and closer to x equaling negative infinity, it's approaching this magic number 3. Remember, limit is a predicted y value. Similarly, on this end, it's also approaching 3. Seems like that might be something important. Guess what we call that when a limit approaches a value? We call it a horizontal asymptote. This is how we will actually define horizontal asymptotes. I'm going to skip that slide. And I'm going to tell you right now in this class, and you probably have heard me say it before, you want to get really good at this class? When you see these little boxes in my notes, you might want to pay particular attention to those because those are the big ideas that are going to help you be successful in quizzes and tests. So if I asked you on a quiz, hey, what's the horizontal asymptote? And you said, hey, it's y equals 3, Mr. Allen. I'd say, great, you're right. Can you tell me why? Well, guess what you'd need to say? You would need to say that the limit as x goes to infinity, for example, of g of x equals what? 3 in this example, right? So this is how we define a horizontal asymptote, which is different than how we defined a vertical asymptote. Back in section 1.5, which was the last section, back in section 1.5, how would we have defined a vertical asymptote? I'll give you a hint. It's a limit as x goes to something of f of x equals something. What does the x down here have to be? X goes to what? Okay, fine. Do you mind if I pick a different number than 0, though? I'm going to pick, let's pick 4, which is different than 3. And then what's this over here have to be? Ooh, this isn't good. We've already forgotten section 1.5. That was the very last section last week. Well, the answer is it has to be infinity or negative infinity. That is how we define, I'll make it negative infinity just to be different. That's how we defined a vertical asymptote. A vertical asymptote had an infinite limit. A horizontal asymptote is when the limit goes to infinity and has a limit. By the way, this is an infinite limit, correct? And let's make sure we're clear. Is infinity a number? No. Okay, good. I will make sure we're clear on that because I'm going to use that here in a minute. Okay, so this slide here tells us how we define a horizontal asymptote, which is different than when we did back in section 1.5, which was for vertical asymptotes. Okay, so I'm going to go over this slide as well. Here's another box, so it's important stuff. And I think that sometimes students see the symbols and it just overwhelms them. So I'm going to give you a concrete example. I'm going to do a concrete example of this one right here. Let's do it in red. So let's say I said that the limit as x goes to infinity. Can someone please give me a number C? And don't pick 0. 4, fine. We'll use 4 again. And can someone give me another number that is a rational positive number? 7. Now we just totally made this up. But here's my question. What is the limit as x goes to infinity of 4 over x to the 7? What is that limit? How do you know it's 0? Because that's what it said, Mr. Allen. It's 0. That's what this box is telling you. Do you remember last week when I did the little pizza thing? I said if I had one pizza and I shared it just with myself, how much of the pizza do I get? 1. Except 1, right? And I said, okay, what if I had to share it with 10 people? How much pizza would each person get? They'd get 1/10, right? What if there was 100 people? What if there was 1,000,000 people? What if there was infinitely many people? And guess what the answer was once there was infinitely many people? Guess how much each person gets? This is that same idea. X is going to infinity. Where's the x? It's in the denominator. So 4 is just a number, but the bottom's going to infinity. It's like, how many pieces of pizza do you get if there's 4 pizzas, but there's infinity people to the 7th power? A 0. You get 0 pizza. Okay? Same thing happens if you go to negative infinity. Does that kind of make sense? And guys, it doesn't matter what this number is up here. If this number had been negative 42, let's say, guess what the answer still is?
A 0.
A 0. Okay? Now, I thought that this would be pretty self-explanatory, but I'm a little concerned because I think students aren't very familiar with this function here. Have you guys seen that function before? Y equals e to the x. If I asked you to graph it, would you know what the graph looks like? I know it's something that we cover in pre-calc, but a lot of students, it's like, they're like, what? Let me sketch the graph here just to make sure everyone is familiar with it. So here's the x and y axis. I'll do the graph in green. And this isn't obviously going to be a perfect graph, but it looks something like this. Does that look kind of familiar to you guys? That's the graph of y equals e to the x. Does that look familiar? So here's what this second part's saying. Actually, let's look at this one here where it's going to negative infinity. Look at the green graph. Where's the graph, the green graph? What y value is it approaching as x goes to negative infinity? It's going to 0. In fact, it never actually gets to 0. That's one of the properties of that. Did you know that? E to the x can never be negative, ever. I don't care how small the number is you pick. Negative 10 trillion is still above 0. So guess what this is saying? It's saying the function e to the x, as you go to negative infinity on the x values, guess what the y values are approaching? 0. And it might look a little tricky over here, but notice they threw that negative exponent there, so they're basically doing the same thing there. Okay? So those are things that you should know. Well, here, let's just do this one real quick. This should be fairly easy. Now think about that graph. Let me sketch that graph again for you here. Remember, here's what the graph is. This function's going to infinity. What's that limit there, part B? 0. Yes, I agree. Do you guys understand why it's 0? What's the bottom going to be when I put infinity into this? It's going to be infinity on, oops, I just wrote E, sorry. It's going to be infinity on the bottom, right? What's the top? It's some constant C. So we're back to that whole pizza thing again, right? If there's 3 pizzas and there's infinitely many people, no one's getting any pizza. A 0. Okay, good. I'm not going to do that. We can talk about that one. We just did it. Okay, and then the last thing I want to talk about today is this box here. Okay. Let me just give you an example of one, and then let's see. I'm going to do some different examples here. I'm going to do this one right here. I'm going to say limit as x goes to infinity well, yeah, we'll do this one here, except now I'm going to put x squared plus 1 over x plus 3. That'll be number 2. Here's number 1, and then here's number 3. Limit as x goes to infinity of, let's do 7x squared plus, Sometimes it does that like horizontal line thing. I'm not sure why it does that. Okay. 7x squared, there's what I wanted, plus 1 over 5 minus 2x squared. Okay. So I got 3 problems here. And this will basically let me know if you understand that last box. And I'm not going to read the last box to you. I'm just going to see if you can just use common sense to figure this out. Can you guys guess what this one is? We just talked about it. It's 0, right? Didn't we just talk about that? So here's what the important characteristic I'd like you to notice is the following. What's the numerator? A constant, right? What's the denominator? It's a polynomial with some x stuff in it, right? So if I go back to this previous slide here, let's see here. If the degree of the numerator is less than the degree of the denominator, guess what the limit is as it goes to infinity? A 0. That's what that's saying. Okay, look at this one here. What do you think this one is? What about 2? Does not exist. Can you give me a better way of saying it? I know I would agree with does not exist. Can you give me a better answer, though, a more accurate answer? Better than that. You guys are right. I mean, technically D and E is correct, but I think you could be even more explicit. No, you're just saying the same thing. I'm going to say this is infinity. Okay. Now let me explain why I'm doing that. Okay. On the top, I'm basically doing infinity squared, right? On the bottom, I have just infinity, right? It is, but I'm squaring the top. Think about it this way. Pretend that this wasn't even on there. What would that reduce to? No, just think of the x. It'd just be x, wouldn't it?
Oh, yeah.
And if x is going to infinity, what's the answer? Okay, so let's go back here. So here's what it says. If the degree of the numerator is equal to the degree of the denominator, is that the case that we have here? Nope, we got this case here. Sorry, I'm reading the wrong one. If the degree of the numerator is greater than the degree of the denominator. Now you guys are saying D and E, which is right, but we could also argue that that's infinity, right? Now the reason I wrote infinity here is the following. What would happen if there had been a negative right there on the top? Then it'd be negative infinity, okay? Now, I claim that this is a better answer, but this is absolutely correct. D and E, remember, we talked about that a couple of slides ago. Infinity is D and E. But D and E is the safest answer, but sometimes we could be a little bit more descriptive, okay? What about this last one? Well, it's going to be this middle guy, the middle one right here. The degree of the numerator is equal to the degree of the denominator, then what you do is the ratio of their leading coefficients. Would you agree that the degree of the numerator is equal to the degree of the denominator? So what's the answer for this limit? -7/2. And if you don't believe me, you can check with your calculator. I can even show you work for why that's true. I could say that 7x squared plus 1 over 5 minus 2x squared, and it did that again, oh well. I could divide through in the numerator and the denominator. Let me write that in a different color here. I could divide through by the numerator and the denominator by x squared. And I'm going to divide the bottom by x squared. Are you with me? So if I take 7x squared, so let's do that in another color even. If I do 7x squared and I divide that by x squared, plus 1 over x squared divided by 5 over x squared minus 2x squared over x. Are you with me? All I've done is I've divided everything in this particular fraction by x squared. Okay, so now what's going to happen when I cancel this guy and this guy? What am I going to be left with? 7. Are you with me? Is anything going to cancel here? Nope. Anything going to cancel there? Nope. Anything going to cancel there?
Yeah.
What?
X squared.
Okay, so I'm running out of room. I'm going to do it up here, okay? So that's going to give me that this is equivalent to the limit as x goes to infinity. I think you guys said 7 plus 1 over x squared over 5 over x squared minus 2. Agreed? What happens to this fraction right here as x goes to infinity? A zero. What happens to this fraction here as x goes to infinity? Zero. What would be left? Now, guys, you don't have to show all that work I just did, but I just wanted to point out where it comes from. This isn't just stuff that like falls out of the sky. There's people that figured it out, and then they write the rules down, and then they verify the rules. Okay. Does that make sense? Questions on any of this stuff? I just went over a lot of stuff. Horizontal asymptotes, and then some of these special rules for how you figure out what limits are as you go to infinity. Because remember, this section is on limits at infinity. Oh, there's one more thing I needed to say. Sorry, guys. I just remembered. Okay. We'll just use this guy right here. What is the limit of this as x goes to, let's say, negative infinity? What's that limit?
0.
It is 0. That's exactly what it is, right? Doesn't matter that it's a negative infinity. It's still infinitely many things, right? Okay, next question. What's the limit of this as x goes to the 0 plus? It's d and e, but can you be more descriptive than that? He's right. When he says d and e, that's right. What's the limit on the right side of 0? It is infinity. Now, in case you're not sure where that comes from, let me sketch the picture for you. This is the graph of 1 over x. We talked about it the other day. It looks like this, and it looks like this over here. You guys remember that? Do you guys understand why this one's infinity? What does this tell us then about the graph? Right. But what does it tell us graphically? You're right. It's going to infinity. That's what it says. But what does it tell us? What's that? Right. So what do we call that? There you go. Thank you. It's a vertical asymptote. That is literally how we define a vertical asymptote, correct? What does this one tell us? Horizontal asymptote. This is a horizontal asymptote. I just misspelled horizontal. You get the idea. Okay? Horizontal asymptote versus a vertical asymptote. Now notice that over up here, I was talking about the limit at infinity, right? And it existed. Down here, I was talking about a limit that was infinity. Does that make sense? This is an infinite limit. That's section 1.5. This is a limit at infinity. That's section 1.6. This has to do with horizontal asymptotes. This has to do with vertical asymptotes. Okay.